Thank you, everybody. It's really a pleasure to be here in Madrid, and I have to say one of the best big data summits I've seen so far. The quality has been amazing, and fantastic crowd, fantastic speakers. So I'll take it straight away. I'm Natalino Busa. I'm specialized in streaming real-time big data, so basically all there is about data, and I'm currently working at ING. ING is a group, is a global financial institution with a strong presence in Europe, but presence extends actually worldwide with more than 40 countries and more than 30 million customers, ranging from individuals to small business to corporates and governmental institutions. So altogether, we'll count to more than 50,000 employees. And one of the slogan, the mission of ING is actually to empower people to stay a step ahead in life and business. And that means actually a number of promises. So to be clear and easy, so banking should be something straightforward, something easy to understand, clear in scope and in the journey for all the products offered. We are living in a connected society, so we also expect financial services to be available anywhere, anytime. And also it means that we also think that customers, they should come with good propositions when it is about data. Data quality and the availability of data should be there to make good decisions, and good decisions are based on data. So empowering the customers by providing data which is up to date and relevant for whatever they need to do. And last but not least, keep getting better when it comes to proposition, customer journeys, security, and in general, all the products which are provided. So I just started from this list of 4, and well, it turns out that actually it maps pretty well to data principles. Since clear and easy, it also would imply that you would have a lean architecture, which is easy to integrate and fits well with the available data which you're going to operate on. Anytime, anywhere, so it should be consistent. We heard a lot of good stories about streaming and real time. Well, that applies also to banking services and also to data available for banking services. Empower, it means to provide relevant, advanced predictive analytics on live data. And that translates almost one-on-one on 2 concepts, event-driven processing and high-quality APIs. And finally, all these should be provided with resilient, distributed, and scalable and maintainable architecture, which is easy to maintain, but also which provides good guarantees in terms of resiliencies and failovers. If you look at data, I think that this picture kind of encompasses it all. You would have big data and fast data, and you could kind of summarize it in 3 main dimensions. If on the on x-axis you put the time, and on the vertical axis you put all your population of events, whether they are transaction, session, customers, and so forth, you would see that sometimes you need to deal with the recent data, and other times historical data is actually relevant because you want to fit some models, you want to see historically how the interaction, the transaction have evolved. Some other times, you just want to follow a specific stream of events, for instance, for a particular customer or a particular set of transactions, and think, for instance, of session data and so forth. Well, those are ideal candidates for event streams. So why fast data? Well, fast data, it's there because we understand that up-to-date information has value. And relevant up-to-date information is what makes most of the APIs today, which we'll all use, the LinkedIn, the Facebook, the Uber, and so forth. And that means that it's able to deliver actionable insights. But big data is still there, and it will still be there. We need to analyze and model our data sets. We cannot learn, cluster, and categorize and organize facts if we don't consider that we have all the data at our disposal. So these two things actually, they need to be combined somehow. And this talk is about how to train, score, and expose models where those two aspects, they come together. And the first component where they come together is actually a data store. So you would have batched data, and you would have streaming data. The very first thing that you can do with just this component is actually to expose those information in terms of API. So you could, for instance, say, okay, whenever a transaction is performed or a new customer is registered, well, that's available via an API. What can we do more if we had, for instance, analytics? Well, what we can do is actually we are able now to model our collection and create, for instance, clusters of customers or of transactions and so forth. That alone will go a long way, and in fact, if you consider data modeling as an operational activity that happens in the bank, then you would have a good, let's say, synergy between storing the data and analyzing the data. But there is a specific category of, let's say, data processing, which actually requires a millisecond response. And for this category, actually, you need an event processing engine. Now, there it comes actually that out of an event processing engine, you would have alerts and notifications. And you could use, in fact, the data store in two ways: to collect the raw data and the events, but you can use it as well to exchange models between a modeling layer or analytical layer and a runtime layer analyzing events one by one. So, in fact, we saw that in the keynote of Paco Nathan yesterday, that actually this combination of components is becoming quite common in many of these, let's say, recipes. You would have a data store component, a fast layer, and an analytical layer. And the reason to exist is that, for instance, if you take this particular set of technology, like Cassandra, Akka, and Spark, you would have, in Akka, you would have very fast processing, so you can go down to milliseconds. It's distributed, and actually you could have very good, let's say, supervision strategies in order to keep the system running even under particular heavy workloads. On the other side, when it comes to a more modern, let's say, approach to big data, you would have Spark bringing up all the data in memory and allowing you to join the data and perform all sorts of machine learning functions And Cassandra, in this case, comes handy as a multi-data center, consistent, tunable, and a replicated data store with very fast writes, but also quite a large throughput when it comes to reads. So if we would zoom in this system, the system actually consists of these three parts. Spark and Cassandra actually can be very closely tied, the one to the other, by using a component called the Cassandra Spark connector. What this connector does is actually able to map partitions in Cassandra to partitions in Spark. And since the two systems are both distributed and both in memory, then becomes actually a very fast way to transfer data from a storage-oriented system to a data processing-oriented system. And Akka there is the layer where you would just, get those models scored and the events produced and analyzed. So if you actually take the perspective of Cassandra is there to store all the data and Spark is there to analyze all the data, then you could consider Spark in orange as a sort of a virtual cluster or another layer on top of the distributed set of rings which constitute your Cassandra cluster. So in fact you could guarantee that the data is stored in a way that is not influenced by the data processing, while the data processing is actually happening on a separate ring or a separate set of machines. So if you kind of break down this system and we just focus for the moment to the Cassandra Spark connection, you would see that you would have the connector taking care that the data is imported and exported from Cassandra by minimizing the number of, let's say, shuffling between the Cassandra and the Spark nodes. Why you want to do that? Because once the data gets on the wire, then it becomes a much slower activity. While if you're able actually to map it in a way that the partition do match, you could actually have the GVMs which are related to Spark and the one which are related to Cassandra actually placed in the same node, sharing the same partitions. So this works very well. However, sometimes you do need to join data, and well, that cannot be done without some shuffling. But then actually the shuffling only happens when you reach the Spark stage. And in that case, you would see that for all the Spark API calls that or methods which are not implying shuffling, then you will still have a local processing. So that means that actually you're doing a very good job and it's going to be pretty fast in this scenario. Okay, so this is an introduction about how would you combine Cassandra and Spark. And now I would like to move back to some application. And one of the most studied, let's say, application that you could have in data science is actually anomaly detection. You'll find in a number of data domains ranging from fraud to marketing to net flow analysis and so forth. And one definition which I find it always a good one when it comes to outlier and anomaly detection is an outlier as an observation which deviates so much from the rest to arouse suspicion as it was generated by a different mechanism. And we had a great talk today by Gene Weber about a different mechanism. Well, that could be, for instance, a set of fraudsters which would mimic the system, but actually producing a completely different set of events or correlated in a completely different way. So when it comes to anomaly detection, there are a variety of techniques, but I think they could be classified themselves into a number of them, and I will present here 5 basic categories. You could go for a model, and this was the traditional statistical analysis. So you would say, okay, this is a Gaussian distribution or a t distribution or a chi-square distribution and so forth. And those actually, they work okay, but they don't exploit the fact that now we have computers. So those were traditional techniques, and they were mostly, you know, pen and paper models. But now that we have computers, we could actually say, why not exploiting the data itself rather than fitting the data to a model? Let's fit, sorry, instead of fitting the model to the data, let's have the data itself coming up and generating a model that actually determines what to do. So going into that direction, you could go for parametric. For instance, box plot is one very simple example of parametric analysis. You could go for histogram, non-parametric. You could go to higher dimensions, and there it goes really into many different directions in terms of analysis. You could go for distance-based, or you could go for density-based. And then there are many more other ways of analyzing that if you move to spectral analysis and subspace exploration and so forth. I will give an idea about what you can do today, and I will use histograms, distance, and density-based analysis in the rest of this talk. Just not to get too much into, let's say, banking data, I think it's a nice exercise, if also for you in the audience, if you want to reproduce some of this technique to take a public data set. And the data set which I've presented here is coming from Gowalla, which was a location-based social network acquired a while ago by Facebook. And their data set is interesting because actually has a number of features which are typical of event processing. So it would have a set of events which are related to when a user actually checks in a particular venue. So you would have the timestamp, you would have the user ID, the venue ID, latitude and longitude for that specific event, and that's pretty much that. So, but still, though the data set actually contains just a few features, you would see that you would come up with a number of very interesting ideas about how to find anomalies and cluster the data. So one way of looking at it is if you would look at it from the perspective of a venue. Some venues, and there is the intuition, would have a weekly pattern of visits which is centered around the midweek, while other venues would be more, let's say, visited during the weekends, right? So in this exercise, for instance, we see Madison Square and the Apple Store in central New York. They pick up around Thursdays and Fridays, while, for instance, the Statue of Liberty and the Javits Convention Center, they seem to be not that popular on Wednesdays. So what would happen is if we treat these histograms as features, we could actually consider that each component in the histogram is a dimension, a feature, and then we could try to cluster together, let's say, venues which exhibit the same pattern by actually looking at how the histogram looked similar, the one to the other. If you would try that, actually you would find a very bad clustering if you just compare histograms, because histograms which have, let's say, a dominating component in a completely different day would still be, let's say, distance equally from each other. So what you would like to do is to apply some distance metrics which actually preserve an idea that similar days are clustered together, and if you have a peak on Saturdays, very different than having a peak on Tuesdays. So there are some metrics there for histograms. For instance, Earth moving distance is one which is quite good for that. Chi-squared. In this case, I just went a bit on the creative side, and I just used DCT as a way to, let's say, modify the domain of the original features, in this case the histogram components, and move to another space, in this case the space of discrete cosine coefficients. So I'll just show briefly what you can do with Spark, and in this case is some Scala code. And this is a typical set of steps that you would do if you are a data scientist. So you would first, for instance, create key value pairs, aggregating by, for instance, the venue ID. And you will start vectorizing and featureizing time. Then you would start creating out of those vectors some form of aggregation. So reduce by key underscore plus underscore simply means I'm now collecting all the vectors for a single venue, and out of that I will get actually histograms. And then what I can do is I can featureize those histograms. And once I've done all that, then there is this library within Spark, which is the MLlib library, where you could actually take those histograms, consider them as features, create vectors of those histograms, and start training the data set, for instance, with k-means. So after you've done this exercise, you would come with a number of clusters. And then you could reproduce exactly the same sequence of steps, rather than this time, instead of training, you would actually take those clusters and use them to score or predict histograms which you haven't seen so far. Once that you have finished this all up, you could actually take the clustered venues and store them in Cassandra. Well, once you have that and you have the models, you have the cluster centers, that's already there, an easy way to apply these techniques to live data. How can you use it? Well, you could use it for classification. So you could, for instance, say, okay, I have a new venue and I don't know what it is. And now I have a cluster of venues that behave exactly like the venue that I'm looking at. So I could use it to classify an unknown venue. So you actually use clustering as a classification strategy. What you can also do, you could use it for anomaly detection. Now, this is, again, it's a good example of how you could come up with robust anomaly detection. Because, of course, like we have seen also today, if you just take a single instance, a single event, it might not be representative for your anomaly detection. I mean, the fact that, for instance, at 8 o'clock in the morning, a particular venue is getting way less visitors than normally, might still not mean that week is anomalous or that venue is encountering a particular, let's say, an anomalous event. But if the entire week aggregated and weighted present a completely different pattern, well, that is actually a very robust signal that something is happening which is not common for that venue. So that could generate an alert. And of course, this example uses weeks, but you can imagine the same things ported back to hour behavior or minutes behavior. And therefore, you can really, if you would have several temporal intervals that you are analyzing, you would have a very nice method right there to reproduce a similar set of algorithms but at different timescales, and actually figure out alerts to use for your, let's say, use cases at different timescales. I want to give a second example which uses clustering, which is now from the perspective of the user. So if actually the user starts checking in particular venues, one thing that you would notice is that users tend to stick to some particular places, and they have habits. So you could start clustering a single user looking at location. This is, of course, good enough for a number of analyses, but you could imagine to extend this idea about, for instance, looking at the location of a certain user in combination with his friends, in combination with users that exhibit the same pattern, or in combination of users that exhibit the same pattern and are friends. So if you start doing that, in fact, you would come with increasingly more and more robust scenarios where actually this data can be clustered. There is a bunch of algorithms that could do that. K-means is actually not particularly great here because K-means are usually create spherical clusters, while in this case it's clear. And by the way, this is the actual picture of extracted from the Gowalla set. This guy is actually spending some time in Georgia and in Florida, and every now and then in South Carolina. Yeah. So a good clustering technique that works here is actually based on density, and it's called the DBscan algorithm. It doesn't even require upfront the number of clusters to be defined, and it works simply by looking at each point, giving a certain radius around that point, and connecting in the same cluster all points which are close to a given radius. So by connecting points, you could imagine, yeah, it's a graph. So yeah, you could actually interpret it as a graph, but in fact, the DBscan algorithm is already good enough for the analysis. So once that you have identified it's blue, it's red, or it's somewhere else, yeah, you would have a good idea about what is anomalous. And anomaly could be a single fact or an event, but it could also be actually a cluster which has fewer events than the bigger cluster. So this algorithm is actually nice because it does not distinguish too much between single anomalies, point anomalies, and small clusters. So they actually are part of a similar scenario. So going back to Scala, if you would do the same with, like we did before, and create pairs, in this case not keyed by venue but by user, and you would take latitude and longitude, you could actually create a combined sequence of all those points and apply the DBscan algorithm to that. This algorithm is actually available in a library called Scala NLP, and it's part of the Breeze library. And you might notice that this algorithm is actually not distributed. What we distribute here is actually the fact that we run the clustering algorithm for millions and millions of users. So we see immediately that even within Spark, you might end up with different clustering algorithms, and in general, it boils down to the point that you actually have an algorithm that requires all the data to be computed in order to come with a result. But there is another set of algorithms that can run independently on millions and millions of users by repeating the same algorithm for a limited collection of events. I think that in Spark is great, and because allows you to do both. There is somehow a tendency to consider that machine learning algorithms are actually only those that would use all the data. But in fact, the power of this sort of ideas is that you can use the algorithms also per key or per collection. And then actually you're much more free to use whatever library it's required to do to clear the job. So MLlib versus pair RDDs, one would be a truly distributed algorithm. You would classify, we've seen for instance classification of venues. You would have a large number of venues, a limited number of clusters or patterns. On the other side, you would have simply the good old, let's say, map or map values, where you would actually take the collection of per key, and then it's an easy to exploit exploitable parallelism, and then you would have much more freedom in the machine learning algorithm you're going to use. So there we have actually our techniques in order to create an event processing system. When it comes to this sort of event processing system, so you actually are solving not one but two problems. You're solving a training problem and you're solving a scoring problem. So what you would notice is that not all use cases are the same. In some cases, it's absolutely fine to say, okay, my training could take hours and my scoring could take minutes. Why not? I mean, these use cases are very valid, and you don't need to let's say, rush or pursue these millisecond sort of scenarios. For those, Spark actually would be a good choice. There comes a point where actually the milliseconds are important, but only in scoring. Yeah. So the training can take hours or minutes, but the scoring must be done in milliseconds. For these scenarios, you could say, okay, I would split the system in two parts. I would have the training done with a big data-oriented architecture. So in this case, Spark is absolutely fine. And I'll do my scoring in a streaming pattern using Akka. You could also say, I need to be fast and I need to exploit the specific online training strategies. So in that case, I would actually use Akka in all the places, even for training. And there are some great papers out there how to create, for instance, training scenarios which are incremental. Like for instance k-means ++, and all sort of techniques based on monoids. So if you have time, have a look at libraries like Algebird, and which actually are able to aggregate and train data online in a streaming pattern. So at the end of the day, the question which we need to ask ourselves is, which processing I'm actually doing on my data? What is the granularity of my data? And okay, what is the trade-off about that I'm willing to take between latency and throughput? Do I need to trade, or I need to have high throughput, low latency? So I need to apply them both. These questions are very, very important, because sometimes we just jump to a data processing platform without actually understanding exactly what are the implications of choosing one platform with respect to another. So one which is really important is, what is my time budget? What is the latency that I can afford in my system? We have seen in the past that MapReduce was going in Hadoop file to file, and writing file and reading file, and it was batch-based. We have seen a certain evolution with Spark going in the direction of in-memory computing, but still applying a similar sort of data flows with RDDs, but it is still big data in the sense that it is a faster implementation. It will use in-memory analytics to do so, but it still is there to process large amount of data. Batch and micro-batch when it comes to Spark streaming. Streaming means, in this case, micro-batches of maybe a few million items, and definitely not in the range of milliseconds, but in the second range. So if this is not enough, you might actually say, okay, I'm going to build it myself. Actually, yesterday we had a few good presentations of companies that said, you know what, I'm just going to take Akka and I'm going to build the whole system from scratch, and I'm going to create my my state in those actors, and I'm going to use concepts like CRDTs or monoids to create my online learning. And it is fast data, and it is event-based. However, it falls again short when you're gonna have to kind of process a large amount of data, because now you're back to the problem: how do I partition my data? How I do my analytics on the big collection? So there are recipes there. Of course, you could say I do Spark and Akka together, or other recipes like the one introduced by Flink. And I think that this mill wheel idea, it's actually quite a breakthrough, in the sense that if I would start from an event and I build it up to macro batches and bigger batches, I actually might have a good shot at keeping the same programming paradigm, and then going for events as well as windows, or maybe the entire data set. So what is important here is actually the users, the developers, the data scientists, the programmers. Those guys, they are actually might have to switch APIs and libraries if you introduce too many components in your architecture. So that's definitely something to keep in mind, how easy it is actually to keep the same computation, the same data science algorithm, and be able to go from batch analysis to micro-batch and to event processing. So since we just went for the let's call it the vanilla scenario. It's a pragmatic approach where you say, okay, I have Cassandra, I have Spark and I have Akka, let's just put those things together. What we still were missing was some form of, let's say, way of connecting together a number of steps in Akka in order to generate scoring data flows. And attach them, for instance, to libraries or systems such as Kafka or APIs or other data store, and produce out again to, for instance, transport streams like Kafka or consumer APIs like, for instance, Elasticsearch or what you have in that scenarios. So. Well, actually, Akka goes quite a long way in defining a pretty flexible actor-based model. What we did was more kind of create a bit of a shell or a wrapper around it so that we could create actors dynamically as, let's say, by means of a RESTful API. So in fact, what you could do is, okay, once that I've wrapped my actor for scoring using this API, I can now directly use web post on HTTP to ingest my new event in the system. And once that I've defined the parameters and the state of this actor, I actually can explore the current state or trigger out events just by using, again, web APIs. So for us, it was actually a good exercise to see whether we could create something where the user could switch on, switch off, modify the input stream, modify the output stream, or provide some, let's say, very fast runtime featureization or enrichment or data mangling on the incoming events. So we open source that is at the moment, yeah, just a small library, so a web API to define, manage, and run streaming data flows, and is built around Akka, and you could use that to access Kafka both as a consumer and as a producer, and also other APIs. So in summary, we have this recipe with 3 components where we have fast analytics in memory using Spark up to the level where Spark is at the moment fit for this purpose. So I would say up to seconds of processing. We use Cassandra as a sort of a impedance adapter, as a sort of a decoupling layer in order to pass around events, but also models. And the event processing part, the millisecond response times, they are offered by Akka and Coral. So a bit of a feedback for the community. So what we've seen is that engineering-wise, Spark, for instance, is extremely strong when it comes to resiliency, checkpointing, and so forth. But we do see that compared to other languages like R or SAS or even Python, actually the number of algorithms is still quite limited. So I would say let's go and in the community and make sure that this actually changes, because we do need more algorithms, we do need more data science. So what about DBscan, optics, PAM, LOF when it comes to clustering? And this is just clustering algorithms. More metrics, more Euclidean, non-Euclidean spaces, tensors, all those great, let's say, instruments that we have in the data science toolbox. We need to exploit them inside Spark. And then why not more let's say, bringing Spark closer to non-distributed algorithms when it comes to run the algorithms, for instance, key by key. What about, for instance, better integration with the Scala NLP or with Breeze and so forth? And last but not least, indeed, a feedback would be we are interested in streaming all the way. And streaming all the way means, in fact, go from hours to milliseconds. If we can actually reuse the same paradigm, and whether that can be done at the moment with Spark in combination to Akka streams or Flink or some other great idea which is maybe etching up in somewhere in the world, I think I don't want now to decide which of those tools has to be used, but I think that we are entering really a domain where streaming is actually something that goes from the single event to the collection of the in terms of petabytes. If we can actually merge and unify this programming paradigm, then I think we have a good shot for the next generation data architecture. So I would say that the future is quite bright for the entire industry when it comes to data processing. And with that, I would like to thank you all for being here.
Question, anyone? We only have time for one question, no? Yeah.
Hi, I was wondering, you just mentioned about Flink, and I was just there on the Flink talk, and supposedly Flink is the tool you're looking for onwards. What's wrong with it in your perspective? Or what is missing?
Missing from what?
From streaming all the way. You were talking about integrated Spark and Akka. Why don't you use Flink instead?
You see, there is a certain pace when it comes to data science and when it comes actually to implement algorithm. And engineering actually goes at a much higher pace than providing viable, solid, robust data products and solutions. So what is missing is basically each time that you switch to the next system, then you have to re-engineer your solutions. Is this possible? Yeah, maybe sometimes it's possible, other times it's not. So while we are actually migrating and we are running this race on engineering and technology, I would like to stand still for a moment and understand how are we doing in terms of data science? Can we port it to the next system because it's greater, faster, more streaming all the way, etc.? Or are we better off maybe, keeping the tempo and pace it out so that we actually can enable those experiences and the products which are exposed by these systems?
All right, so that's all we have time for. Thank you very much. Natalino has been very pretty advanced. So thanks a lot.
Thank you.